Chapter 7a is titled Analytic Trigonometry. In this chapter, we'll take a step back from graphing trig functions and we'll utilize several identities to simplify and evaluate expressions and equations. If you take a look at these 5 different types of either identities or relationships, we have reciprocal identities, which hopefully would look familiar to you as we've worked with reciprocals before. But then we have some new identities. We've got Pythagorean identities, which are kind of like Pythagorean theorem with trig definitions. We have 2 quotient identities. We have odd-even identities, and then we have co-function relationships. What we'll do with these sets of identities and relationships is simplify expressions, and like I said before, evaluate and solve equations. What I mean by simplifying expressions is utilizing the identities maybe in different ways or in different orders. For example, if you see an expression 1 minus cosine squared theta, that looks like it would match up with Pythagorean identity in some way. That has a cosine squared and a 1 in it. But if it's 1 minus cosine squared, that means they took the cosine and subtracted it to move it over. And if you subtract it to move it over, what would you have left? You'd have sine squared. What that means is 1 minus cosine squared theta could be rewritten as sine squared theta. That's a squared right there. But the thing we have to be careful about is if we have just 1 minus cosine theta, that doesn't equal just sine theta. We cannot square root each side because of that subtraction. So we just have to be careful with what ways we can interpret it and what ways we can't. That being said, let's take a look at that expression or that equation in more detail. The plane sine squared plus cosine squared theta equals 1. How can we rewrite that in as many different ways as possible? If we think about the expression that we just worked with, 1 minus cosine squared theta equals sine squared theta. What if we switch that around? What if we said 1 minus sine squared theta? What would that equal? That would just be cosine squared theta. All I'm doing is taking the original Pythagorean relationship and moving some things around. If we said, if we flipped it around like sine squared theta minus 1, we'd have to move the 1 to the left, but then the cosine over to the right, and that would make that cosine negative. So just different kind of ways to work with this. We could also do cosine squared theta, and if I move 1 to the left, I'd have to subtract it, which means sine would have to be subtracted to be moved over to the right. Just different ways to interpret that one definition. But there are so many others to work with. Using all the identities and relationships up above, can we simplify or fill in the blank with these expressions down below? So it says use the identities to fill in the blank. The first expression, sine theta times cosecant theta. Well, if we look up above, right away we see reciprocal identities with sine and cosecant. Sine theta, if we leave that as is, times the first reciprocal definition is that cosecant equals 1 over sine theta. If you multiply sine by a fraction, just put sine over 1. Notice the sine is on top and on bottom. That just cancels out. And you have 1 over 1, which equals 1. So sine theta times cosecant theta equals 1. And hopefully that makes sense. Any reciprocal times the original value would always equal 1. All right, let's try another one. The next one, cotangent squared equals. So I see a cotangent squared up above under the Pythagorean identities. It says cotangent squared A equals cosecant squared A minus something. Well, if we look back up at those definitions, it looks like they took the 1 right here, right here, and they just moved it over to get cotangent by itself. That would mean down below, to fill in the blank, we would say it's cosecant squared A minus 1. We just took that Pythagorean relationship and manipulated it just a little bit. All right, let's try that last one in this top row. Cotangent B times sine B. Well, if I look at the reciprocal identities, I don't see a connection with cotangent and sine. So if I go over to Pythagorean, nothing's being squared, but then look at the quotient identities on the top right. If cotangent B could be rewritten as cosine B divided by sine B, and then we multiply by sine B over 1, the sines would cancel and we'd have cosine B divided by 1, which just equals cosine B. We simplified that product down to one term. All right, let's keep going. We have two more in this section. Secant squared theta minus 1. So when we see secant squared theta, I see that squared and I think to myself that must be a Pythagorean relationship. If it's secant squared theta minus 1, it looks like they took the 1 and just subtracted it to move it over. So then what you'd have left is tan squared theta. Like so. And then our last example, E, sine of angle R divided by cosine R. Well, sine and cosine aren't reciprocals. Nothing's being squared. But if you look at the quotient identities, I see a definition for sine divided by cosine. That's the same as tangent. That means sine R divided by cosine R is equal to tangent of R. Just using the identities up above to simplify different types of expressions. So that's the new information for lesson 7.1, day 1. The rest of our content on this page is all going to be review. We're going to start with a little bit of review from chapter 6a, looking at what quadrant makes sense for the given information. When we did this before, the first step was sketching the triangle in the correct quadrant. So I've added that chart with pluses and minuses as a guide to help us. It says if secant u is equal to -3/2 and tangent of u is greater than 0, determine the values of the other 5 trigonometric functions. Secant is negative. So if we recall, secant would be the same as, or the reciprocal of cosine. So if secant is negative, cosine is also negative. So if cosine's negative, we know we can be in quadrants 2 or 3. But then it says tangent is greater than 0. That means tangent has to be positive. And tangent's positive in 1 and 3. So that means quadrant 3 is where we'll draw our picture. To start off, remember we just sketch a location, and I'm going to draw that triangle by taking the center and just drawing a hypotenuse somewhere into quadrant 3. But I'm going to have to move my paper over just a little to get everything to fit there. Okay, we're back. Always connect it up to the x-axis and form your right angle. Your theta, where we measure all of our definitions from, is always in the center of the graph. So there's kind of our template. Secant is the reciprocal of cosine, so that means it's hypotenuse over adjacent. The hypotenuse, remember, always is positive, no matter what quadrant you're in. That makes this length right here +3. Adjacent is the side that connects to the x-axis, and that's going to be the 2, but because you're counting to the left, it's -2. Hopefully this is looking somewhat familiar from what we did a couple of chapters ago. Before we can find the other 5 trig functions, we need to find the length of the missing side. We'll do a little Pythagorean theorem to help us. I'm going to take the adjacent side and call that my A. The B side is what we're going to find for the y value, and then the hypotenuse is 3. -2 squared is 4, and 3 squared is 9. If we move that 4 over, we get b squared equals 5. So we're not going to get a perfect square, but when we take the square root, b will equal square root 5. If you label that over on that left-hand side, we have to then figure out in that location in quadrant 3, should that be positive or negative? Hopefully you remembered that the y value would actually be negative. So put a little note right there, remembering what quadrant you're in, if side lengths are positive or negative. Once you know all 3 sides, then this should be completely repetitive for you from what we did back in chapter 6a. We know secant, let's find the others. I'll start with sine of u, and that equals opposite over hypotenuse, or y over r, and that would be -square root 5 over 3. Cosine is just the reciprocal of secant, which is adjacent over hypotenuse, negative 2 over 3. Tangent is opposite over adjacent, which would be negative square root 5 over negative 2, and those negatives would cancel, square root 5 over 2. Now we have secant as a reciprocal, but we need the other two. The reciprocal for sine is cosecant, and here's where we're going to run into a little trouble. That's hypotenuse over opposite, so we're going to get that square root in the denominator. Let's rationalize that quick. It doesn't take us long to do. Remember this, the negative is going to stay in the answer, and we have 3 square root 5 on top, and the square root of 5 times itself on the bottom is just 5. We have one more cotangent at u, and that's going to be 2 over square root 5, the reciprocal of tangent, and then we rationalize it. And that'll be 2 square root 5 over 5. We're not going to do too many of these, but having the location is going to help us with new definitions that we get later on in the chapter. And now we're going to go back even further than trigonometry. We're going to do a little bit of factoring review. We're going to factor trig terms in this chapter. Factoring is just like what we did with quadratic functions from either Algebra 2 or functions class. You always want to check for a common factor first. And a common factor could be a number or a variable or a trig term that all parts in the expression have in common. Here's our example, 4x minus 12. To factor this, I see that there are two different terms, 4x and plain 12. We can't factor it with x squared because there isn't an x squared, so really all we get is a possible common factor option. Think about what could go into both 4x and 12. They both have a common factor of 4. So 4x minus 12 would equal 4 times something left over. Remember, factoring is just products of smaller parts to equal the original expression. If we factor 4 out of 4x, we just have x left over. Minus, if we factor 4 out of 12, 4 goes into 12 3 times. There's your factored form. But then we'll kick things up a notch and have quadratic expressions with, believe it or not, trig terms eventually. If you have a quadratic expression in the form x squared plus bx plus c, where there isn't a coefficient in front of the x squared term, you're going to want to factor the constant to get the coefficient of b in the middle. So this will probably be the most familiar form of factoring that you think about when we talk about factoring. It says factor x squared minus 9x plus 20. Since there isn't a number in front of x squared, we're going to factor 20. Lots of numbers going into 20, but we want to figure out what two numbers would actually give us negative 9 when we combine them. Factors of 20 include 1 and 20, 2 and 10, and 4 and 5. Oh, that 20 looks kind of goofy, doesn't it? Let's rewrite that there. Out of these three pairs, can you think of a pair we could multiply to get positive 20, but also add to get negative 9? If we make 4 and 5 both negative, they would multiply to be positive 20, but then add to get that negative b value in the middle. This means x squared minus 9x plus 20 is factorable into two smaller parentheses. The x squared should split up into the x and the x, and then the 4 and 5 are both negative for the second part of each parenthesis, and that's called the factored form. It's that last form where there's a number in front of x squared, that a value, where we need to multiply a times c and then split to get that b value. So there's a couple of ways that factoring works for these kinds of expressions. I'll show you the way that we talked about it in our functions class, but if you have a different method that works for you or you know a different method that's just more efficient, I'm totally on board with that. I just want you to be aware. If it says factor 4x squared plus x minus 3, the 4 out in front is going to play a significant role in our factoring steps. The first thing you want to do is multiply 4 and 3. Actually, 4 and negative 3. So take the a value and then whatever the c value equals. 4 times negative 3 is negative 12. And that's what we want to factor to try to get the b in the middle, the number right in front of x. Technically, the number isn't written, so it's plain 1. We need to try to figure out how to get positive 1. Factors of 12 include 1 and 12, 2 and 6, or 3 and 4. Now, one of those numbers will have to be negative to get negative 12 when you multiply. Which pair would work so that when you add them, you also get positive 1? If you think negative 3 and positive 4, you're in great shape. Once you know this pair, go ahead and set up your two parentheses. X minus 3 and x plus 4. Here's the tricky part. From here, think about, okay, there's still that 4 out in front. We need to work with that in some way. At this point, you divide those two values by 4. If you can reduce the fraction, you absolutely should do so. But in that first parenthesis, 3 divided by 4 doesn't simplify. Therefore, the 4 is going to go in front of the x, giving you 4x minus 3. That would be one of your factors. In that second parenthesis, the 4's would cancel out to equal 1, and that would then leave you your second factor. There's the factored form when you have that a value in front of x squared that isn't 1. It does change how we separate the terms. And last but not least, sometimes you'll just have two terms in a quadratic expression and they're both perfect squares. When that happens, it is factorable to two parentheses. The first squared term just splits up into its normal set of parts. But that second squared term, you take the square root of it and you get just the plain value for that second term, or that second part of the parenthesis. What makes this unique is that you're going to have a plus and a minus in between them. All right, so let's see how this last part's going to work. For the first example, factor 5x squared minus 20. Well, so here I'm kind of throwing you off right away. There's an x squared term, but the 5 and 20 aren't perfect squares, so that doesn't make sense. Unless you think about that common factor. 5 actually goes into 20. What that means is we can factor the 5 out before we do anything else. If we factor out the 5, we get x squared left over for that first term, and 5 goes into 20 4 times for the second term. And now 4 is in fact a perfect square. 4 can be rewritten as 2 squared. And once you have two perfect squares, you can split up your two parentheses. The x squared would split up into x times x, and the 2 squared would just be 2 and 2. And then one of them's plus and one of them's minus. And it doesn't even matter what order you put those in. Always remember to put that common factor out in front as your final answer. Over on the right, I put this one in here specifically because students will want to try to factor when it's addition, but it actually doesn't work. If you have addition instead of subtraction, the two parenthesis rule with a plus and a minus won't give you positive 16 when you multiply. So this one is not factorable because of the addition. And there you go, everybody. That's our lesson for 7.1, Day 1.